All right, in this example, we are going to start taking a look at finding our regression equation. And again, that regression equation is going to be the equation of the line that best fits the linear relationship between two quantitative variables. And so remember, we are looking at data that when we plot our two variables, that data does look linear. And so that's why we're going to use a linear equation to model the data set. You'll notice we did put a little hat on this y value. That shows that for any given x value, the y value that we get that goes with it is a prediction or an estimate, not an exact point. And remember, that's because these points fall roughly scattered about a line, something like that. They're not all perfectly on the line, okay? So what you'll see for the remainder of this first page is just our instructions for finding the line of best fit using the TI84. So I'm not going to take much time to go through all of this. We're going to go through it as we do the example on the next page. So we're going to start off with the same example that we used to find the scatter plot in the last video. So this is a data set on education, so number of years of education, and then annual income for a group of individuals. So because we already did the scatter plot for this, just as a reminder, it looked like this. And we know that those points look linear. We are comfortable going ahead and finding the equation of the line that best fits those points. This is called the line of best fit. Again, sometimes it might be called the linear regression equation or the least squares regression equation. So the way that we find that is we are going to hit stat. And remember, we've already entered our x values here into list 1 and our y values into list 2. So those are already there. So we're going to scroll over to calculate. So we did stat, calculate, and we're going to scroll down here to option 4 that says LINREG, which stands for linear regression, and we're going to hit enter. The calculator is going to verify that we did in fact put our x values into list 1 and our y values into list 2, which we did. And so we're going to scroll on down to calculate and hit enter. And here's what we get. So we have y equals a, but they're telling us a is 10.36 if we round to 2 decimal places. So 10.36x plus our constant here is a negative 107.31. And so that's our equation that would best fit this data set. I'm going to put this in terms of some variables that make a little more sense for this data set. So I'm going to call y years of education, and I'm going to call I annual income. And so what we would be saying here is that our annual income can be predicted, remember we're predicting, by taking 10.36 times our x values, those were years of education, minus 107.31. And I'm not trying to confuse you by using a y here. I just used y for years of education and I for annual income. Okay. Next, we're supposed to use our regression equation from part A to predict the annual income of someone who has 16 years of education. So 16 years of education means that our value for years of education, which we called y here, is 16. And so we're just going to plug in a 16 there. And we can do this in the calculator. So we're going to have 10.36 times 16 minus 107.31. And that gives us 58.45. And remember, those are in thousands of dollars. So if we multiply that by 1,000, that's $450 is our prediction of the annual income for someone who has 16 years of education. Next thing we're going to do is interpret the meaning of our slope. Remember, the slope is the number that comes in front of the input variable. So in this case, that's 10.36. Whenever we're interpreting a slope, we're going to write it as a fraction over 1. And remember that slope is always changing your y value over changing your x value. So in this case, our y value was annual income. And our x value was years of education. And so the reason it's nice to write it that way is now you can see what we're saying is that as our input variable, years of education, goes up by 1, our output variable, annual income, goes up by 10.36 thousand. And so we would say for each additional 1 year of education, annual income is expected to increase as well, increase because our slope was positive, by approximately, remember this is a prediction, an estimate, by approximately 10.36 thousand, which is $10,360. Okay, so that would be our interpretation of the slope. For each additional 1 year of education, annual income is expected to increase by approximately $10,360. One definition here that we need to talk about is something called extrapolation. And when you use your regression equation or your model to try to predict values for your output variable, for values of the input variable that are far outside the original range of inputs, you can end up with poor predictions. And so what we're talking about here is if you go up and you look at our data set, our original years of education were between 12 and 24. So we had data for individuals that had between 12 and 24 years of education. So what we're saying down here is if we tried to use this model that we just created, here's our model. If we tried to use that model to make predictions for income for people with years of education that are not within that 12 to 24 years of education range, we could get some really unusual and incorrect predictions for their annual income. And a place that you can see that happening is when I ask you, is it appropriate to interpret the meaning of the vertical intercept? So remember, the vertical intercept would be the value of annual income when your input variable, years of education, is 0. So 0 years of education, you can tell, is not close to within the range of 12 to 24. So in this particular case, trying to use our model to make a prediction for annual income of someone with 0 years of education is an example of extrapolation, since 0 is not close to our original range of x values. If we had a data set where we had data close to 0, then interpreting the vertical intercept might be perfectly fine, okay? In this case, you can tell that vertical intercept is when years of education here is 0. We're saying that the predicted annual income is negative $107.31 thousand. So what we're saying is if we were to go and try and interpret that, it would be saying that if you have 0 years of education, that your annual income is going to be approximately negative $107,310, and that certainly doesn't make sense. So when it asks us, would that be appropriate, we would say no. 0 years of education is not close to within the original range of values. So this is extrapolation. Okay, and this should make sense, right? As we get further and further away from the data that we know, it becomes more and more difficult to predict. So for example, if I asked you to predict the price of a gallon of gasoline tomorrow versus predict the price of a gallon of gasoline a year from now, it would be much easier and you would be much more likely to be accurate to predict the price of a gallon of gasoline tomorrow. And that's because it's close to the data you do know, which is today's price. If I asked you to predict for a year from now, and all you know is today's price, that becomes a lot more challenging. So that's kind of the idea of what we're saying here with extrapolation.